This exercise is a little bit longer than a lot of the other exercises in this book, but it's a really insightful exercise. It's going to demonstrate to you the importance of using more numerically stable algorithms for computing least squares. So we're going to compare the explicit inverse and NumPy's least squares and stats models least squares implementations. And I think you might be surprised at some of the results from this exercise, and I'm pretty sure that it's going to be enlightening. Okay, so continuing with the model from exercise 2, and by this I mean the design matrix that includes rainfall and temperature in degrees. So not rainfall in seasons like we used earlier, but rainfall and temperature. So starting from that model, what you are going to do is create a new design matrix that contains a fourth regressor. So you're going to make up a new regressor, and that is going to be some linear weighted combination of the other regressors that are already in the data set. So somehow, randomly combine, linearly combine temperature and rainfall to create a fake fourth regressor in the model. Now, that means that the design matrix is going to have 4 columns, but a rank of 3. Okay, so yeah, you want to confirm this and also compute the correlation matrix. And here I'd write a little bit about interpretations, which I'm going to talk more about in the code. Okay, yeah, but here you see it has 4 columns, but a rank of 3. Okay, and then you want to fit the model using 3 different approaches. First is the direct implementation of the left inverse. Remember, this is actually the implementation that we used in the previous chapter to implement least squares. So literally just implement the left inverse. And then use the least squares function in NumPy, or maybe this is pronounced square, which obviously stands for least squares. And then also use the stats models library. Okay, so for these 3 different approaches, you want to compute the R squared and the regression coefficients, and then print them out. And basically, yeah, okay, I don't want to talk about this now. I'm going to talk about this more when I produce these results in code. And I'm also going to talk about this paragraph down here. Okay, so now I will switch to code, and we will work through this solution. Here is where I create the linear combination of these 2 features in the design matrix. So I came up with some random linear combination 4 and 0.4. You can come up with any numbers you want. You can just generate these as random numbers, or put numbers in here as I do. The only thing that you do not want to do, so the only restriction, is that this needs to be a linear combination. If you make this a nonlinear combination, we're still going to have a design matrix of rank 4. So as long as this is a linear combination, you're good to go. You can do anything you want. Okay, let's see. Here I recreate the design matrix. Here I'm adding the intercept. And then here I'm augmenting the design matrix. So I'm adding on an extra column, which is this lin combo variable here. Okay, and then I'm just printing out the size of that matrix and also its rank. And then here is the correlation matrix. Now, let me zoom in here a little bit. So again, yeah, here, this is what I showed in the book. Now, just a quick note about interpreting the design, the correlation matrix of the design matrix. This column corresponds to the intercept, right? So we have rainfall, and then temperature, and then the intercept, and then the lin combo variable, which is just a combination of these 2. Now, the intercept itself does not have any variance. There's no variability in the intercept. It's 1 for every single row. So that's why the correlation matrix prints out NaNs, because we end up dividing by a 0 because of the normalization term in the correlation coefficient. You'll remember that from earlier in the course. So if there's 0 variance in a variable, then then we have 0 in the denominator. So we end up with something that is illegal in the world of mathematics. So that's just one thing to to be aware of. Another thing I would like to point out is that you don't see any 1s in this correlation matrix, except for the diagonals, which are trivially always 1. every variable is perfectly correlated with itself. But this last column here and this row here, this is the perfect linear combination. This is why we have a rank 3, and yet we don't have any perfect correlations with individual variables. And that's because this variable doesn't only come from one variable, it comes from a combination of multiple variables. The reason why I want to discuss all this is that looking at a correlation matrix is great. I encourage it. It can be really insightful. It can help identify problems, or it can help you interpret the results, but it's not a suitable method to see if there are issues of multicollinearity. So yeah, there's a problem with multicollinearity, but there's nothing wrong with the correlation matrix. Okay, so all of that said, let's see. This is just another way to print out the correlation matrix using pandas, and then this method .core at the end. I guess I should have talked about this. This just looks prettier, right? It's just nicer to look at. All right. Anyway, here we are using the left inverse. Now, here's the thing. This design matrix transpose times itself. We know that it's a 4 by 4 rank 3 matrix. It does not have an inverse, and yet I am inverting it here. So this is the left inverse. I mean, it's not the true left inverse because this is reduced rank. But anyway, and then, yeah, let's see. So here's where I compute the beta coefficients and the predicted model data, and then the model fit. Now, when I run this code, I get an R squared of 0.1, which is actually not so bad, right? You remember the previous models, the fit was much worse. So, 0.1, initially, if you're not paying any attention, you're just looking at this, you might think that a R squared of 0.1 is pretty decent. I would like to point out that this is a non-invertible matrix. It's a singular matrix, and yet when I run numpy.linalg.inf, I don't get any error messages. I don't get any warning messages. And yeah, so here, if you're curious, you can read more about this. It's been reported as an issue. Some people, including myself, do not think that this is appropriate. In my opinion, if you are trying to invert a singular matrix, then Python and NumPy should give you maybe not an error message, but at least a warning message. There should be a message that says, hey, pay attention, you're probably getting junk results. But anyway, so something to be aware of about NumPy. All right, so here we're using the listsk function. And yeah, it's not a whole lot interesting to say here, except you do see that the R squared jumps up to 0.3. And here is using stats models. And notice again here, we have to explicitly add a constant to this model here. Okay, so now I'm going to just print out all these results as I showed in the book. And yeah, what you see is that the least square method in NumPy and the stats models routine give identical results, 0.3126 for the R squared. And you can also see the beta coefficients are exactly the same. And even though the model is the same, the design matrix is the same, the theoretical math is the same, and the data are the same, the left inverse method gives a lower R squared and just bogus result. I mean, these are ginormous numbers. They don't make any sense. If you're curious, you can plot the observed data by the predicted data, similar to the plots we created in the past exercise and earlier in the book. And you will see that the left inverse method is just junk. It's not trustworthy. And yet, again, like I'd mentioned before, there's no error message, no warning message. Python just did it, even though it doesn't really make sense, and the result is unreliable. In my mind, this highlights two important features of applied statistics. One is that these are the mathematical bases, but in practice, I've said this before, but this is the sort of thing that you use when you're learning about statistics. But then when it comes time to applying statistics, you use more numerically stable methods like this or stats models library. So that's one thing. The second important take-home message from this exercise is that understanding the math of these analyses is so important because you're not getting error messages, you're not getting warning messages. And so if you don't understand the math of least squares and just in general statistics, then you might be doing incorrect things. You might be getting incorrect, uninterpretable results without realizing it.